Hello and welcome to this lecture on models of a fluid at rest. Now we are going to look at ideal gas equation of state. This lecture is in continuation with the various previous lectures that have been delivered on fundamentals of thermodynamics. So before this lecture comes a series of lectures which put together the thermodynamic framework, and now we are going to develop a model for one particular type of system called an ideal gas, and then we are going to employ this model as well as the framework to obtain the various properties, thermodynamic properties of an ideal gas. So in doing so, the effort will primarily be from entropy perspectives, thermodynamic perspective, though there will also be initially we will start with what is called the kinetic theory of gases, and therefore from the kinetic energy and the momentum transport perspective. But I will not take that to its logical conclusion. I will at some point jump to the thermodynamic perspective, because though the model is introduced from this perspective, since this lecture is part of a series of lectures in thermodynamics, so the whole last part of the lecture will fully be from thermodynamics perspective. So to give a sort of a sense of where we are and what the goals are, in order to develop the model, a model for the energy of a system, we reviewed the fundamentals of thermodynamics so far. Having put in the framework of thermodynamics, these lectures are analogous to another series of lectures where we considered the continuum model of a flowing fluid, right? A series of such lectures, and then now we finally turn to the models themselves here. So we only looked at the framework of thermodynamics, we have not looked at the model of a fluid at rest. We finally turn to the models themselves, and we are considering four models of a fluid at rest. One is a model of an ideal gas mixtures. This will be a two-part lecture. The first part of the lecture would be on model of an ideal gas, and then the second part would be on ideal gas mixtures. And as you know, to get a little bit ahead of myself, ideal gases are gases where molecules have no form of interaction with each other. In other words, there is no potential energy of interaction. Remember, in the internal energy that we defined, it is the sum of all the potential and kinetic energies of all the constituents of the system. And in an ideal gas or an ideal gas mixture, for that matter, there is no potential energy of interaction. So this is only purely a kinetic energy based. You know, the energy stored in the system is only by virtue of kinetic energy. And so to sort of give a contrast with another model of a gas where there are some interactions, some potential energy of interaction is accounted for, the other model to consider would be van der Waals gas or gas mixtures. That will be a separate lecture that will be recorded separately and uploaded at a different time. Then we look at a model of an ideal liquid slash solid, actually, to be frank, and of course, similar to gas mixtures, we will have ideal liquid mixtures. Liquid mixtures are often called solutions. So this is a model of a condensed phase. So this is a model of a gaseous phase, this is a model of a condensed phase, and this model can be taken up for either a liquid or for a solid. And then we take up models of liquid solid mixtures where there are you know, significant interactions between the various constituents of the system. Of course, in any condensed phase there is significant interactions, So when we discuss this regular solutions, we will address what is meant. So but this will sort of be a contrast to the van der Waals, somewhat along the lines of different from the ideal gas to van der Waals gas. Like that, we'll have ideal liquid to regular solution. So these four models will be considered for a fluid at rest, and the goal is to develop the model in each case and then use the framework of thermodynamics to obtain the thermodynamic properties of such systems. We start with an ideal gas. Wikipedia defines ideal gas as a theoretical gas composed of many randomly moving point particles that are not subject to interparticle interactions. Now, this is very interesting. There are lots of interesting phrases here. First is that of a theoretical gas. In other words, this is an idealized limit of a gas. There is no such gas that is really exactly an ideal gas. And the gas is comprised of many randomly moving point particles, which means the volume occupied by each gas molecule is taken to be 0, and they are not subject to any kind of interparticle interactions. So the key concepts in this definition are, of course, also random motion, in other words, unbiased by itself. Point particles, that is, volume of each particle is negligible, and no interparticle interactions, therefore no potential energy stored in the system. The model of an ideal gas can be viewed or developed from two perspectives. One is from the kinetic energy perspective. This is from the transport picture, arising from momentum carried by the particles and the momentum flux of the particles, which should lead to pressure, right? So we saw in the development of continuum model of a flowing fluid, that the momentum flux, the convective momentum flux is essentially pressure. The other perspective is a thermodynamic perspective, starting from entropy, where you consider the multiplicity of microstates or molecular arrangements corresponding to n point particles which are occupying a volume V. And that's all we need to consider, because they don't interact with each other in any possible way, and therefore there is no bias coming from there, right? So this can be either done in a continuum picture, where there are so many continuous states that are available, or you can look at a simpler lattice model, and as has been our our approach with earlier lectures, we always go for the simplest possible model, which will capture the essential physics of the system, and it will give us the most significant outcomes it will predict correctly. So we will go with a lattice model. So we'll, as I had mentioned, we'll start with the transport perspective, but then we will not take this to its logical conclusion. At some point we'll just jump and then move into thermodynamic perspective, and then come back and connect the two together. It's a bit of an unusual way to do it, but I believe it's at the level that which I'm pitching this lecture, I think this would be appropriate. So the final equation, of course, result is of course going to be the equation of state, PV-T relationship of the ideal gas, the very popular ideal gas equation of state. PV is equal to nRT, where N is the number of moles of the gas, R is the universal gas constant, temperature T, volume V, and pressure P. So now we start with system specifications. The so-called kinetic theory of gases is founded on the following assumptions about the system. The system is this ideal gas that is contained in a macroscopic container. System is a macroscopic system. The gas comprises very small particles called molecules. The molecules of the gas, the individual molecules of the gas may be modeled as quote-unquote solid, rigid, identical spheres, each with the same mass m, each with characteristic dimension radius much smaller than those of the container in which the gas is stored. This means this radius is going to be, or size of each sphere, right, quote unquote solid sphere called this molecule, is going to be much smaller than the size of the container, and therefore one can approximate this to be zero, tending to zero. This means that the volume occupied by all the gas molecules, which is excluded to other gas molecules. So each gas molecule is occupying a certain volume in which some other gas molecule cannot come and occupy, right? So that volume is often called excluded volume, right? This volume is negligible compared to the volume of the system. And so we take the extreme limit of saying that this radius is actually zero and that the excluded volume is actually zero. So the entire volume of the system is available for occupation for all the gas molecules, even though there are already molecules that are occupying a certain actual physical volume, rigid identical spheres of certain radius. In other words, as I said, the entire system volume V is accessible for all the gas molecules at all times. And the number of molecules is so large, macroscopic system, that a statistical treatment may be employed. Now, we are going to try and specify the state of the system. The molecules do not interact with each other. Therefore, they do not exhibit forces leading to potential energy stored by virtue of their relative positions. So, whenever they exert forces, they don't exert a force on another molecule by virtue of the relative position of that molecule with respect to the first molecule, and therefore there is no potential energy that is stored by virtue of relative positions. Thus, the internal energy of the system is equal to the kinetic energy of all the gas molecules. Now, I am talking a little bit thermodynamics here. All right. The molecules are in constant motion and travel only in straight lines, since there are no external forces to curve their trajectories. So in the absence of an external force to curve the trajectory, the molecules will always tend to take the shortest path, and that would be a straight line. The molecules will collide with the wall of the container in perfectly elastic collisions, and therefore we are saying that there is no loss of energy due to these collisions. The time taken for collision is negligible. In other words, all collisions are instantaneous compared to the characteristic time between successive collisions. So the molecule spends so long moving from one collision to another collision that the actual time it takes for each collision is negligible. Further specifying the state of the system, since there is no external force at all changing the momentum of the molecules, the net momentum flux, which is simply the force per unit area, rate of change of momentum, by the way, is force, and rate per area is flux, and therefore net momentum flux is simply force per unit area, which is pressure. This may be found out simply by the pressure exerted by the molecules on the walls of the container, which are surfaces which are impermeable, rigid and adiabatic. Again, I am throwing some thermodynamic terminology in here. So in other words, the molecules cannot escape from the diffuse through the surface. The surface itself is rigid, it's not going to move, and there is no exchange of energy with the surroundings. Therefore, the average kinetic energy of the gas molecules is due to the existing inertial state of motion. Now, you look at Newton's law. What does it say? Newton's first law of motion. All bodies will continue to be in their state of rest or uniform motion, the existing inertial state, unless there is an external force that changes that particular inertial state. And since there is no external force changing the existing inertial state of these gases, so the average kinetic energy of the gas molecules is only due to the existing inertial state of motion. The molecules are in some state of motion and they continue to be in that same state of motion, which is characterized only by the temperature, and of course again I'm throwing thermodynamics here, and temperature and entropy of the system. Note, the number of collisions between molecules is negligible compared to the collisions the molecules have in the container walls. In other words, say suppose there is one wall here, let this be one of the walls and let this be the other wall, right? So this lighter colored region is the space where the gas molecules are, and the darker brown colored regions is the wall, so to speak. So suppose my laser pointer is a gas molecule. It goes and collides with the surface here, and it's an elastic collision, so it bounces right back. Now on the way it goes all the way back here for a collision again, all right. Then in this intermediate path, there is hardly any collision with another molecule. That number is very, very negligible. So in other words, there is always a clear path. Suppose the collision the molecule comes and collides at an angle like this at the surface, and then it will be bounced back, reflected back, and then it will then be colliding here, and then it will go back here, and then it will go back here, and then it will come back here, and then it will go back there, and so on and so forth, right? This kind of continuous path that the molecules keeps taking, all right, it hardly ever collides with another molecule. What does this mean? This means that the density of the gas has to be very small. In other words, the number of molecules in this volume is so small that there is hardly any collision between the molecules. And these, by the way, are important assumptions. We will come back and see that there are limitations. Only under such assumptions, such conditions will this model actually hold. And we will discuss that later. Now, with this system specifications, we start developing the expression for momentum flux and kinetic energy of momentum flux being pressure, right, and kinetic energy of these gas molecules. So for this, we consider an ideal gas of n gas molecules, capital N gas molecules, each of mass m, enclosed in a cubical container of volume L cube. So this is L, that is L, and that is L cube. And this molecule is moving at a certain velocity, in that there are three components: X component, Y component, Z component, depending on the coordinate frame. And then this is basically your, each of this is a surface, and the surface area is L square. So what is the pressure exerted by the gas molecules on the walls? Suppose we are considering this X plane. This is the X plane. This is the Y, Z. This is the Z, and that's the Y. So that's a YZ plane, which is the X plane. What is the pressure exerted by the gas molecules on this plane? So suppose a gas molecule I, out of the n molecules, ith molecule comes and collides upon the wall on this surface with a momentum given by mvxi. Since the collision is elastic, it rebounds back with a momentum minus mvxi, right? So the net change in the momentum is 2 times mvxi. So this one minus the other one, right? So 2m into vxi. The time between this and the next collision, remember, one of the assumptions is that there is hardly any intermolecular collisions. So the number of collisions between gas and the walls is much larger than any collisions between molecules, and therefore if this molecule came and banged right horizontally onto this X plane, and then it got bounced back with momentum minus mvxi, it is going to go straight here and go bang at the minus X plane, right? So the time, the distance traveled basically is L plus L, 2L, between two successive collisions, or rather 3 collisions, right? After this collision, it went here L, and then it came back 2L. So the time between this and the next collision is simply 2L by Vxi, because there is no change in momentum, and therefore you can just write time as distance by velocity. So rate of change of x momentum, which is the force exerted, all right. So that is net change in momentum per a certain time, and that then becomes mvx square by L. Okay, so that is what this force exerted on the x plane becomes. So the total force exerted on the x plane for all molecules is then, you have to multiply by the you have to add up the forces exerted by all the molecules. And so if Vx square bar is the average of the square of the velocity in the x direction, so this is the mean square velocity, right? And then average velocity times the number of molecules. So this becomes the total force exerted on the x plane. Since this motion is completely random, there is no bias in any direction. Of course, so far we have considered only one direction, which is the x direction. Similarly, there could be collisions along the y direction, collisions along the z direction, and you can have collisions that can be resolved into components where there is Vx, Vy, and Vz and whatnot. But the random motion implies at least that the average squared speed is the mean square velocity in each of the directions should be the same. So by Pythagorean theorem, the net speed is net mean square speed is simply the sum of these three. Therefore, since these are all equal, so the mean square speed in the x direction is simply the net mean square speed by 3, right? So 1/3, 1/3, and 1/3 gives the total. So therefore, if I were to convert this, expression, the force exerted on the x plane with respect to the mean square velocity, then I have to replace mean square velocity in the x direction by mean square velocity divided by 3, and that gives my total force exerted on the x plane. So what is the pressure? What is the flux of x momentum? That is force per area. Area is L square, and therefore I get n m v bar square v square bar by 3 L cube. But L cubed is the volume of this cube, that is the volume of the system, and therefore n m v square bar by 3v is the pressure. That is the pressure in the x plane. Since the motion is random and unbiased, the blood pressure in the y plane and the z plane are all identical. It's the same isotropic pressure everywhere, and the subscript xyz may be dropped, and therefore the average momentum flux or the average pressure exerted by the molecules on the container walls is simply this pressure, which is nm v square bar by 3v. The average kinetic energy is, of course, half into m into v square bar. So therefore, you see that the net kinetic energy of the system is related to the product of pressure and volume. This is an important conclusion. PV is given by nm v square bar by 3, which is 2/3 of kinetic energy, 2/3 of half mv square bar, right? This is an important conclusion. Now, this conclusion has some consequences. Pressure, volume are macroscopic properties. So here, what have we done by developing this model? We have essentially related some macroscopic system properties to mass of a molecule, right? And the v square bar, which is the velocity of the mean square velocity of a molecule. These are molecular properties. So basically the macroscopic properties have been related to molecular properties. This is important. This is of particular importance. Now, what is left to close this loop is to relate the mean square velocity and therefore the average kinetic energy of the molecule to temperature. Now that would require us to come up with a perspective of temperature from the kinetic theory standpoint, from the momentum transport standpoint or transport standpoint. But you know, since we are in the midst of a thermodynamics discussion, I'm going to take advantage of that, and I'm actually going to sort of, after this slide, pretty much abandon this approach and then move on to thermodynamic approach, and we will try and obtain the average kinetic energy from entropy, all right, and then tie in the two perspectives together, the transport perspective and the thermodynamic perspective together. So the average kinetic energy of the molecules may be obtained by maximizing the multiplicity or entropy of the system. So far we have considered a continuous distribution of n gas molecules in a volume V with a range of velocities. Of course, you can't have any velocity less than 0, and you can't have any velocity greater than infinity. So that's the range. You know, theoretically, that's the range. The number of molecules having a velocity 0 or velocity infinity may be negligible, or 0 literally. Nonetheless, that's a range. So this unbiased maximum entropy distribution of velocities is given by what is called the Maxwell-Boltzmann distribution. I'm not going to discuss this at all. In fact, this can be obtained from principles of statistical mechanics, but that is not the objective of this lecture. So we go for a very simpler, much simpler model. Here f of v, by the way, is a continuous probability distribution of the continuous random variable v, because v can randomly vary between 0 to infinity, such that you integrate over the entire volume, all right, integrate over all possible velocities, both should be the same, that the total probability should be 1 for all the molecules in the system. So this is the distribution, but we are not going to discuss this. For ease of understanding, we have so far considered simpler lattice models and thereby discrete distributions, which capture the same essential physics to understand entropy, and we are not going to do any different now. So let's now consider a simple lattice model for the ideal gas, where we consider the volume V to be made of some arbitrarily defined m lattice sites. So the volume occupied by each lattice site is V by m, right? The question that we have to ask is, what is the multiplicity W in distributing n particles? Remember, we started out with the model of n gas molecules, so n particles in m sites. Entropy as defined by Boltzmann is S is equal to K ln W. So what is this multiplicity? N particles in m sites, so m factorial by n factorial times m minus n factorial is your W. Okay, so ln of W, you can just put this, substitute the W multiplicity value into the logarithm, and then of course you can expand this out by saying S by K is ln m factorial minus ln n factorial minus ln of m minus n factorial. This, however, gives S as a function of m and n, not v and n, so to speak. So we have to convert this whole lattice picture of m sites into a volume of v, right? And that is where we basically go use the chain rule. So then we say dou s dou v at constant n is dou s dou m at constant n times dm dv. Of course, this is not a partial differentiation. This is ordinary differentiation, because this is a direct relationship volume V is made of m lattice sites. So dm dv is simply m by v. All right. So so this is basically the inverse of volume occupied by each lattice site, right? So therefore, if we can get this expression, then we can go and get that expression, and that is related to thermodynamic pressure, isn't it? So with that, we can obtain ideal gas equation of state. We can obtain basically a relationship between pressure, volume, and temperature. So now what we are going to do is we just have to, in order to evaluate this, first we need to evaluate logarithm of a factorial, and for that we are going to use Stirling's approximation. This is valid when the numbers involved are large, and of course, since we are looking at Avogadro numbers of molecules, obviously m has to be much larger than the Avogadro number, because remember that the density of the gases is very small, and the gas molecules hardly encounter each other, and therefore there must be so many empty unoccupied sites, and therefore the both m and n handily satisfy the requirement for using Stirling's approximation. Therefore ln of n factorial can be approximated as n ln n minus n. So therefore S by K is given by m ln m minus n ln n, and then this will get cancelled, minus m minus n ln m minus n. This minus n term and minus m term will get cancelled with this, the term that comes from m minus n factorial. So using Stirling's approximation, we obtained an expression for S over K, which is n m ln m minus n ln n minus m minus n ln m minus n. Now we can take a derivative of that entropy with respect to total number of lattice sites m at fixed n. The number of molecules of ideal gas is fixed. And remember, the expression was for S by K, so S is equal to K times that those ln terms that we had. So dou S dou m at constant n, you may work this out, and it simplifies to minus K into ln of 1 minus n by m. Now we know from the thermodynamic perspective that pressure exerted by the ideal gas on the system boundaries, container boundaries, is given by P by T is dou S dou V at constant UN. And of course U and N are fixed because the boundaries are both adiabatic and rigid. There is no exchange of energy with any surroundings by heat transfer, and the boundaries are rigid boundaries. Therefore, the pressure exerted by the ideal gas on the container is simply given by this, okay, where what has happened, we have taken dou S by dou M at constant n, and to get dou S dou V, we multiply that by dm dv, which is simply m by v. So this term expression has been taken. This is P by T, so P is equal to P into dou S dou V at constant UN, and therefore the temperature shows up here. Now expanding the this logarithm as a Taylor series, ln of 1 minus x is minus x squared by 2, and so on and so forth. For very small densities where n by m is much less than 1, keep in mind this is a measure of density, because m is the total number of lattice sites, n is the number of gas molecules, and the assumption that we have made in developing the system specifications is that there are very few gas molecules in the volume. That is why if you consider this to be the light colored central region to be the container, and the dark colored boundaries to be the container boundaries, then basically what we assumed was that there is very negligible number of collisions between molecules when a molecule travels from one collision with one boundary to another collision with the other boundary of the container. And therefore, that implies that the number of molecules is much smaller than the number of lattice sites inside the container. And therefore, since n by m can be taken to be much smaller than 1, and this simply becomes ln of 1 minus n by m is simply minus n by m. So that basically gives P is equal to nkt by V, where n is the number of molecules, k is Boltzmann constant, P is temperature, and V is volume. So this is the fundamental PV-T relationship for an ideal gas. So we have obtained what is called the ideal gas equation of state, PV-T equation of state. If we define the gas constant R is Avogadro number times the Boltzmann constant, then we get P is small n RT by V, where this small n is the number of moles of gas molecules in the container. R is the gas constant. Small n times R is equal to capital N times K, where n is the number of moles of gas, that is given by n by the Avogadro number, with this being the Avogadro constant. So thus we have obtained the ideal gas equation of state. Now, comparing this result that we have obtained from the thermodynamic perspective with that of the kinetic or transport perspective, we observe that PV is n by 3 into mv square bar, which is now n by 3 into 3 kt. Okay, so because this is simply nkt, so I have just written it as n by 3 into 3 kt. And therefore, the average kinetic energy of a molecule may be seen to be 3 by 2 kt. So half m v bar square is 3 by 2 kt. So if you have n such molecules, the internal energy of the system is n times the kinetic energy of each molecule, average kinetic energy of each molecule, because there is no potential energy of interaction in this model that we have considered. And therefore, U is simply 3 by 2 nkt, which is 3 by 2 nRT. So this is a very important result for ideal gas equation of state, that U is of internal energy is a function of temperature alone, and it is independent of pressure. This is important to keep in mind. Now let us ask ourselves, what is the relationship between internal energy and degrees of freedom? A monatomic ideal gas, a single atom ideal gas, has 3 translational degrees of freedom. It cannot have any rotational or vibrational degrees of freedom because it is a single spherical molecule, really, the way it has been modeled. If the total kinetic energy is 3 by 2 kt, then how much energy is available for each independent degree of freedom, each of these translational degrees of freedom? There is a theorem called the theorem of equipartition of energy, which also arises as a consequence of maximizing entropy, which we will not derive or discuss in great detail. The theorem states that molecules in thermal equilibrium inside the system, in other words, temperature is uniform everywhere in the system, have the same average energy associated with each degree of freedom of their motion. So by partitioning the available energy equally amongst all degrees of freedom, you maximize the entropy, and this is something that you can intuitively relate to. So the distribution that is there, that is available, if you can distribute it maximally out, to all the micro states or microscopic arrangements available, the energy dispersal is maximum and the entropy will be maximum. That is what theorem of equipartition of energy states. And therefore, that means that for a monatomic ideal gas, the average kinetic energy associated with the translational motion in either the x or the y or the z directions is each half kt. So if for an ideal gas, if there is an arbitrary f degrees of number of active degrees of freedom, then the internal energy should simply be F by 2 NKT or F by 2 nRT. So with this understanding, we look at diatomic and triatomic ideal gases. In deriving the ideal gas equation of state, we considered only the translational kinetic energy of the molecules. The reason for this was that we assumed the molecules to be rigid spheres. Suppose we have diatomic molecules like oxygen or nitrogen. They have 2 additional rotational degrees of freedom. Consider a triatomic molecule such as sulfur dioxide or carbon dioxide. The molecule has rotational degrees of freedom and 2 additional vibrational degrees of freedom, in plane vibration and out of plane vibration. These additional degrees of freedom are shown in the following picture. This is the rotational degree of freedom. So it can either be rotated like this or into the screen, so to speak, right? Similarly, there is a vibrational degree of freedom. This is, one vibration is in plane, one vibration is out of plane. From the equipartition theorem, the expressions for internal energies of diatomic and triatomic ideal gases would then be, for a diatomic ideal gas, there are 5 degrees of freedom, 3 plus 2. And for a triatomic ideal gas, again additional 2 more vibrational degrees of freedom. So for the internal energies would be 5 by 2 nRT and 7 by 2 nRT respectively. So at this point, I want to sort of make an observation. So we have obtained developed the model of an ideal gas from both from a thermodynamic perspective, strictly speaking, and some insights have also been drawn from the transport perspective. Now I have really not gone into drawing an analogy between these 2 perspectives and seeing where, if any, there is any difference, where the 2 perspectives differ, diverge, and all that. But we have the end result that we have obtained is a PVT relationship for an ideal gas. That is the ideal gas equation of state. PV is nRT. Now, having gotten that, we obtained the expression for internal energy of the ideal gas. Whether it is a monatomic or a diatomic or a triatomic ideal gas, we obtained the expressions for internal energy, and we observed that internal energy is only a function of temperature. It's independent of pressure. And I want to sort of spend about a few seconds discussing what is the implication of internal energy being a function of only temperature and not a function of pressure. When I say it's a function of temperature, temperature captures the average kinetic energy. As we saw, half mv square bar is half kT. So, 3 by 2 kT, right? So it captures the average kinetic energy of the molecules in the system. To get the potential energy, you should look at what is the force exerted between molecules, and therefore we have to look at some sort of an internal pressure, right? And that since that potential energy is not there at all for an ideal gas, internal energy happens to be independent of pressure. We will see that enthalpy is also independent of pressure, right? So this is one part of the picture. Now, in the thermodynamic framework, in the last few lectures, we looked at various thermodynamic properties which we obtained expressions for. So between now and the rest of this lecture, we will be looking at how we can take this expression PVT relationship as well as the expression for internal energy of an ideal gas and then obtain various thermodynamic properties of the ideal gas. So we start with enthalpy. So for an ideal gas contained in a system with moving boundaries, or for ideal gases in flow, pressure is the independent variable instead of volume. So the appropriate thermodynamic potential would be enthalpy. Enthalpy of an ideal gas is simply given by H is U plus PV. PV we know is NKT or nRT, and therefore this is F by 2 nRT, and this is 2 by 2 nRT, and therefore the enthalpy is simply F plus 2 by 2 nRT. So therefore monatomic, diatomic, triatomic gases enthalpy is given by monatomic ideal gas 5 by 2 nRT, diatomic ideal gas 7 by 2 nRT, and triatomic ideal gas 9 by 2 nRT. And we again see that enthalpy is also a function of only temperature for an ideal gas. After completing the entire recording, it turned out that the whole lecture is so long, so I have decided to split this lecture into two parts. This itself is already 45 minutes. So the second part will take up specific heat capacities, heat capacity ratios, PVT relationships for adiabatic processes of involving ideal gases, various expansion, compression properties of ideal gases, entropy of an ideal gas, Gibbs free energy of an ideal gas, chemical potential of an ideal gas. So those will be discussed in the second part of the lecture. So this split is done post recording the whole lecture, and therefore if there is any break in the transition, I apologize, but I hope this helps in processing of the whole content a bit easier. So as always, if there are any questions, I'll be very happy to address them. Please feel free to send your comments and feedback and your questions on the either on the YouTube page or through my email ID, which is available at the website, whose link is provided at the about part of the YouTube page. Or if you're already a student of my class, then you know how to reach me otherwise also. So thank you for listening to this lecture. Have a wonderful day. Thank you.